My name is Tom, and in this video I am going to show you how to find what is known as the normalizing constant in the context of probability. In many books you will see a question that says the following: find the constant c such that the function is a probability density function. Okay, so let me write this so it's more concrete. So I'll use some colors here, and at the end we'll take a look at a picture and we'll take a look at the whole process. Say you're given the following. Okay, this is kind of like the first transition step from discrete random variables to continuous random variables. Okay, being able to find that c. So you may be given a function that looks like this: f of x equals, and then you're given c times x, and this goes between 0 and 2, and the function is 0 otherwise. Okay, that's what the OW means. Otherwise the function value is 0. So the first step is to find that c. Okay, that c will make the area under the curve equal to 1. That is its purpose. That is what we mean to say by normalizing. That means the area will be equal to 1. Just let me highlight that. Here we are. Okay, so that c will make the area under the curve x here equal to 1 between 0 and 2. So how do we actually go about finding it? Well, we apply one of the fundamental concepts, okay, of a continuous probability density function, which is the following: the area, the integral, if you like, under the area under the PDF has to be 1. So in symbols, what we have is the following: we have this, and this goes from negative infinity to positive infinity, of f of x dx equals 1. Okay? So the area under the curve, that's what these symbols indicate, is equal to 1. And the way to ensure that this is so is to actually take your c and find it. We'll solve an equation that will give us c. So let's translate these symbols and connect them to this more concrete and specific example, which looks like the following. The integral in our case will go from 0 to 2, because that is what we are told in the statement of the exercise. The c stays. We do not know what c is, so we simply keep it. We cannot replace it with a number just yet. And the rest of it is just x dx. Okay? And all of this, in order for this function to be a PDF, has to be equal to 1. Okay, so this is simply saying that the area under this curve must be 1. So here now you have to draw upon your knowledge of integration, specifically the power rule, and make the observation that the c with respect to the integral is constant, which means you can pull it from the integral. Okay, so pull the c out, and then what's left is the integral from 0 to 2 of x dx, and all of this still equals 1. Okay? So let's work on the integral part. What we have is the following. You've got your c, and then what you have is, by the power rule, 1/2 x squared between the limits of 2 and 0. And all of this still equals 1. Now we replace and evaluate, so we still have the c on the outside. And then we have 1/2 of 2 squared minus 1/2 of 0 squared. All of this equals 1. So let's simplify the quantity between the parentheses. So you're keeping your c the entire process. Okay, and then you've got here 1/2 of 2 squared. Well, 2 squared is 4. 4 divided by 2 is 2. So that's how you get that 2 that I've just written. 0 squared is 0. 0 times the negative 1/2 is still 0. So from the parentheses here, all that remains is the positive 2. And all of this still equals 1. So we are just about done isolating C. And now we observe that the operation between the C and the 2's multiplication, the opposite or inverse operation is division. So we divide both sides by 2. By 2, which means, lastly, that C equals 1 over 2. This is our normalizing constant. This is the number we multiply the function by to make the area under its curve equal 1. So that it's a probability density function and not just some random function. So this means the following. Let me separate our work here. Okay, so this is complete. Step 1, you have found C. Step 2 now, well, let's rewrite this function so it's more concrete. Which means f of x, now we know that this equals a half of x between 0 and 2. And we know that it's still 0 otherwise. Okay, so this c that we have replaced is now 1/2 of x. You see? So we've gone from not knowing c by taking this step of integration and solving for c. Now we know that c is a half, and that is known as the normalizing constant because it makes the value of the area under the curve equal 1, which means the total probability, of course, is 1. That's what it means. Geometrically, it guarantees the area as 1, but in terms of probability, it means the total probability is 1. And now let's use this, right? This may be the first step in an exercise of this kind in a textbook, and the second may be the following. Actually, once you have found this, find the probability, right? They may give you a part B to the question that says find the probability that the following. 1 is less than x, and that is less than 2. Okay, so find the probability that our variable x assumes values between 1 and 2. Okay, that is what we have to do. Find that probability. So how do we do it? Well, we simply integrate. Okay, so this is what we're going to do. Set up our integral from 1 to 2 of the function. So it looks like this. And this will tell us the area between 1 and 2 under the curve. It's also equal to the probability that x is between 1 and 2. So the 1/2 is once again constant. Pull it from the integral. It doesn't depend on where you are along the x-axis, so you pull it from the integral. Okay, so this gives you now this x dx, which now gives 1/2. You apply the power rule, so you have 1/2 of x squared, evaluated between 2 and 1. Okay, so it looks like this. Continue simplifying. 1/2. And notice that the 1/2 is present here, which means you can pull that 1/2 out also. So pull it out as this, 1/2 times 1/2. Plug in the upper limit and the lower limit and subtract. So 2 squared minus 1 squared. This gives 1/4. 2 squared is 4. 1 squared is 1. Which means now you have 3 over 4. Okay, so the probability that x lies between 1 and 2 is 3 over 4. That is what this number tells us. And now let's take a graphical interpretation of this problem. So what are we going to do? We are going to draw an x and y coordinate plane. Okay. We are going to draw the PDF. So the PDF is 1/2 x. Okay. So that means, in other words, 2 to the right and 1 up. So 2 to the right and 1 up. And then another 2 to the right and another 1 up. So it looks like this, okay? So our PDF, and what we have just found, is the following. Okay, this is like a picture of the PDF. It looks like a triangle drawn this way, okay? In the second part where it says the integral between 1 and 2, let's draw another picture so they don't get cluttered together. Okay, and let's change the axes just a little so that it's easier to visualize this. Let this be 1, and this is 2, this is 3, so this is 1, and this is 2. Let's draw the PDF again. So the PDF says 2 to the right, 1 up. Okay, so it looks like this. And this one here is the area between 1 and 2, so that is this area here. Okay, there we are. This is a common exercise in many calculus-based probability books. Here x is a continuous random variable and not a discrete one. So one more time to review, remember you are first given this in many books. You have to find a normalizing constant c, which means you set up this and you set it equal to 1 because the area has to be 1. You pull this c out, you perform the integration to get c equals 1/2. You can now write the specific, more concrete version of the PDF as follows. Then the probability, the next question many times, of course, is, use this function. The probability that x lies between 1 and 2 is given this way, and once again you have to integrate. So the probability that x is between 1 and 2 is the integral of the PDF between 1 and 2. So you pull the 1/2 out, apply the power rule. The second 1/2, where the pen is pointing, pull that out also, so it gives you 1/2 times 1/2. Replace the upper limit of integration, so it's 2 squared. Replace the lower limit of integration, so it's 1 squared. Now you have 1/2 times 1/2, which is 1/4. 2 squared is 4, 1 squared is 1. And at the end, you have simply 3 over 4 as the area between 1 and 2 under the PDF that I'm pointing to right now, okay? That's the meaning of this. But of course, on a test, you might have to write the probability that x lies between 1 and 2 is 3/4. And there you go. Thank you for watching.